All right, so let's resume the lecture, second part, and start talking about multiprocessor, because this is basically what you have nowadays when you buy a CPU, right? You have multiple core. So multiprocessor 101. It's, if you think about it, right, the reason why we have multi-core processor is actually because, I mean, obviously we can make a single core faster, right? Make a better branch predictor, have more cache, make a deep pipeline so that you don't have to stall. This would improve application performance, right? And then if you think about it, all applications that run on that computer would share this one single processor. And as it gets faster and faster and faster, at some point you probably need a nuclear reactor to power the computer, which is not something that's power efficient at all, right? So around year 2000, around the time where we have dual core processor, the market, like Intel and AMD, come up with a solution, say, hey, instead of making a single processor faster and faster and faster as it consumes more and more power, why don't we just add more processing core? I mean, you don't have to make it fast, but you have to basically stamp out 2 copies of those core on your CPU, right? And the core would share some of the resource in the memory hierarchy. For example, you can have a full core system, each with its own private L1 cache, right? So each core would have its own cache, and you have a shared L2 cache and a shared memory. And that is something viable, and it's something common, right? Your computers likely have this similar structure, right? And now you have multiprocessor. You have 2 core. You have 4 cores. You might have 8 core or 6 core, right? Your server is likely to have 32 to 64 core per node, right? Each core, to improve utilization, one thing you can do is to, well, make sure a separate program run on each of those core. This is called multi-program. Because it's coming from different programs, there's no sharing of resources, right? So they can run independently and they'll just use this shared DRAM, share L2 cache, but there's no data sharing. The key here is no data sharing. The second idea is you can write a parallel program, because, I mean, at some point you might want to make sure your program runs fast, right? And it runs on multiple cores at the same time. So you can write multi-threaded program. And now the data is shared across a number of threads, and the program inside each thread can read and write to the same data, because this is data from the exact same program, it's just from different threads, right? So here are the key issues in multiprocessor. First of all, you have only one DRAM. Yeah, only one shared L2 cache. You have 4 or 8 cores. The first question, how should I share the resources? How do I prevent one application to take up all the resources so that the other application cannot run anything? How to ensure data coherency? Data coherency means that when you want to access the data from different core, it should have the most updated version of the data. How do you ensure data consistency in the memory, in the sense that if certain sequence of read and writes occur to the main memory, how can I make sure that everyone sees the same sequence? How to schedule what to run and when at what core from the OS point of view. So now we'll first talk about the first 2 issues here. How do I share resources and how I can prevent application from taking all the resources, right? So the first thing is we want to share resource while we want to manage application interference. When you look at application interference, let's say you run 2 programs. Say you have Chrome, right, with YouTube. And then let's say the other application is Spotify, right, running on your desktop. And if you open up 500 different Chrome tabs, what might happen to Spotify? You have Chrome opening up with YouTube and multiple other things on Chrome, PDF reader built in on Chrome that try to go and access Google Drive to open some PDF file. At the same time, you're opening like 5 different other papers so that you can make some reference and you're listening to Spotify. They all share DRAM, right? They share the main memory, which means that there has to be some policy to make sure that Chrome doesn't take up all the resources, which sometimes it did, right? And that's when your computer gets really, really slow, right? So what can we do? Let's say you have multiple apps running, right? Every single application, by default, they use the main memory, right? And by default, they issue the cache access. So they need to access the cache. They need to use the memory. So when you have more and more application, there'll be more people wanting to access the cache. There'll be more people wanting to access the main memory, right? So if you think about it, but again, some applications are more demanding than the other. For example, if you are trying to play a game, the application might demand a lot of the GPU resource. For example, it might need more memory to process some of those graphic rendering, right? Some application can use up all the cache space, evicting everyone else's data from the cache, right? Because the way cache work is simple. It's say, hey, LRU policy, the least recently used block would be in the cache. So I run multiple applications. It turns out one of the application access cache a lot, and it kicks everyone else's data from the cache. One application have a really high row buffer hits that prevent other application to access DRAM. The problem, right, with these kind of situation is then the other program would take even longer to process, load, and store. You might run into the case even when you have unpredictable load and store latency because you have other applications using your resources, right? So these are the shared resources, typically your cache and your DRAM, right? So handling the cache interference when one application use the cache is there have been people proposing, right, that say, hey, maybe we can partition your cache by saying, hey, let's say I have application A and B running. I will add n ways to application A. And if I add that, application A would give the performance improvement, but it's going to be different from the other application because they have different utility. If I give one application more cache, the amount of performance improvement I see will be different from the second application because no A and B are not the exact same application. There's this thing called performance cliff. For example, you have a nested loop, right? For example, you have nested loop where you have the outer loop for, and in there you have the inner loop for, right? If you can cache everything in the inner loop, it's good, right? But then the more you cache, you're gonna see a cliff where the benefit doesn't improve much until you can actually now cache everything in the both loop, both nested loop. In that case, right? It may be a good idea to figure out, hey, where's that cliff? So I know how much cache can I give to this application? Should I give the innermost loop only? Or should I cover the entire footprint of both loops, right? So the first idea is called cache partitioning. It ensures that each application can only take, say, n ways of the cache, right? Let's say it's 8-way associative cache. It means that for each cache set, each application can take n ways. This can be assigned statically, or this can be adjusted dynamically. All right, unless you have lots and lots of application, it means there's somewhere certain share amongst different applications. So here are the benefits. The benefit is you have some form of isolation, right? So this means that you reduce interference. So for application data that are important, you can put that in the way that's specific to you, for example, to make sure that it will not be interfered by other applications. The second idea is also, if you look at application characteristics, they have different affinity to the cache replacement policy, right? Some applications are more LRU friendly than other applications. For example, if you have streaming application, you can prefetch them, right? And do not promote them. So because if you have streaming application, what are these? These are something that looks like I have access, right, to this block, followed by the next block, followed by the next block, followed by the next block. But there's no reuse. We keep going, which means that if you put that in the cache, there's no benefit of having them in the cache because I don't touch that address again. So the idea maybe is to prefetch, put them in the cache actively, and keep them in the LRU so that they get evicted right away. If you have hot data means that the data get used often. You try to put them in the cache, or cold data that the data is not used often, just evict them right away, right? You can also have something like a victim cache, which is kind of like a pseudo cache that only take in block that have high reuse, right? It has a lot of access to that block, but it also get evicted often because of some reason. We call that block a victim. It's a good block that get kicked out because someone else tried to kick it out, right? Then we can use the information that, hey, I've been to the victim cache. It will then tell the main cache saying, hey, don't evict this block. Don't evict this block. We can use the victim cache as a way to hold information for the cache. You can also have a fully functional tiny intermediate cache layer acting like a victim cache as well, right? To reduce interference, there's also hash bypassing. Basically, if you know that the application doesn't really benefit from the cache, go straight to the memory. Don't use the cache. This would yield the cache space for other application, right? You can look at cache insertion and eviction policy. For example, you can look at, hey, maybe we can use multiple policy depending on the property of the cache and the application that are running on it right now. And if the application can use LRU and it use LRU well, use LRU, or you can use the random policy, right? For example, you can also look at, hey, maybe we can insert thing and insert cache block in a different way. Some of them can go to LRU, some of them go to the MRU position to make them less likely to be evicted. You can perform cache partitioning by looking at the utility and partition the cache for each of the application, right? You can also look at things like bimodal insertion policy, where there's some probability I insert the new cache block at the LRU position. I can have the dynamic insertion policy where I would pick the better of the normal MRU. I have new access. This new access is the most recently used. So that's the MRU insertion policy. And the bimodal policy. And the decision can be done through the process called scheduling. Some set will use MRU, some set will use BIP, and then policy for every other set will follow whoever wins, follow whoever has the least number of cache miss. So that's also possible. Think about it, right? You build something complex in the hardware, but the policy is actually pretty simple to implement. You have the leader set and you have the followers, and the follower set just get the use the better of the two, right? You can look at re-reference insertion policy. Basically, you try to insert the block near the NRMRU list, and you use a multi-bit version of the not recently used policies. This is a hierarchical not recently used policy we talk about during the caching lecture. And when you touch the cache line, you reset the counter. Otherwise, for the other cache line that is set, you increase the counter. And then you evict the line with the maximum number of counter. This will try to imitate LIU, right? And initial value can be max -1, right? So if you are curious, this is one of the policy that was kind of focused on 10 years ago in terms of implementation to the real chip. It's called RIP. There's a paper on that on our reading list, actually. This eliminates the fact that if you need to implement LIU, you need a list. Now you don't need a list. You just kind of imitate LIU using not recently used policy. All right. You also can partition the ways, as I mentioned, right? So, for example, you can try to compute the utility of each additional cache associativity given to the application, right? To do that, it means that you have to have a way to track how much utility I got, right? So the idea of this paper proposed a structure called a shadow cache, which is a tag structure. So it doesn't contain any data. It doesn't contain the data, the full-blown data of the cache. It just has the tag structure for the L2. And it would estimate the hit rate for that application if the application is assigned n ways of the L2 cache. This would collect it, the UCP would collect the stat and reassign the number of ways according to the data. So these allow you to basically perform set sampling. You don't have a full-blown tag array. You only sample some sets, and this shadow cache can be much smaller, right? So that's about managing the cache through insertion, eviction, and partitioning policy. You can also perform prefetching. Prefetching talks about, can I put the data I know I will access in the future into the cache ahead of time, right? Recap, compulsory miss are misses where it's the first time I see the data is definitely a cache miss. So the idea is maybe it's possible to predict the address before I need to access the cache. Based on the history, right? I would try to predict where do I go next. For example, if it's a program that accesses the data in the linear fashion, then you can predict what addresses you are likely to access. And it is pretty common, right? So because a lot of times you write a code like this for I equals 0, I is less than n, I plus plus, and you do something with the array A at location I. Right? This means that the array A, the access to array A will be super linear. It's A0, A1, A2, A3, A4, A5, A6, A7, and keep going on, right? Then you basically then know essentially when you have to access, say, A100. You know when you access A150 based on the history of your accesses. You can also try to look at graph traversal and see if you can predict the addresses, for example. Because when you add some position, you kind of can predict the node that you are likely to visit next, right? And the solution is basically, can we determine the address and bring this data into the cache beforehand in a timely fashion so it doesn't bring the data in too early or too late. If it's too early, the data can get kicked out. If it's too late, by the time you need the data, it is not there, right? Some of the design issue, the prefetcher has to be accurate. You want to prefetch the correct address. You want to make sure the data arrive at the correct time, and you want to make sure it's bandwidth efficient. You don't issue so many prefetch requests to the point that it just flooded DRAM, right? So these are the issue. And you can look at stream of Stride Prefetcher, not last semester, sorry about that. So Stride Prefetcher, basically, let's say you detect a pattern A plus n, followed by an address A plus 2n, followed by the address A plus 3n. N is a stride, which means that the next address is likely A plus 4n, followed by A plus 5n, which means that your prefetcher can predict that pattern. It can pick up that pattern and say, hey, I would just fetch A plus say 6n, 7, and then 8n, right, into the cache. You can also look at Markov Prefetcher that utilize a Markov model to establish the probability of my access to certain addresses for future data access, right? The downside is this actually pretty costly because you need to predict and maintain a bunch of data in order to keep up with the addresses, right? The next idea is called SMS or spatial memory streaming. So the observation is many commercial workloads have correlation, not just branch correlation, but the data address correlation. So we can use repetitive layout that cover a huge region of memory in a similar fashion as you look at branch predictor, those like two-level predictor. And so the idea is basically, can we maintain a pattern of history table that store the repeated pattern and its associated address? This idea is proposed by Steven Smoky at ISCA 2006. It's called spatial memory streaming. It proposed this active generation table where each entry in the table, right, store the tag, the offset to the tag. For example, let's say you have access to A plus 3. Pointer option. Okay. You have access to A plus 3 plus A followed by A plus 2 followed by A plus 0, and you have eviction of A plus 2, right? It basically means that this is the pattern you're likely to see. So it first store, right, A as a tag, and then the offsets of 3, and then the pattern you have A plus 3, which is these are the bit patterns. So for A plus 3, it knows that it accesses the plus 3, right? Followed by the plus 2, followed by the plus 0, and then you evict. So this gives you the history pattern where whenever you see address A plus something, initially you get A plus 3, which is this guy. Then what you need is going to be the pattern that access this, which is the first bit set. This is A plus 0. This 0 is A plus 1. As you can see, there's no A plus 1 here. So the table will tell you, hey, you have to prefetch A plus 0, A plus 2, and A plus 3 without the need to prefetch A plus 1. This, once you have eviction, then you have the future, the pattern history table that now store whenever you see A plus 3. Whenever you see A plus 3, get A plus 0 and A plus 2 with them, because that's the prediction. So when you have the prediction, you have this spatial pattern that tells whether you need to access A plus 0, A plus 1, A plus 2, A plus 3, A plus 4, blah, 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 up to here, right? Up to the length of the spatial pattern. And you check the program counter. If it's matched, the program counter that store the pattern with the same tag, then it would predict and take the spatial pattern and get the address that you want. If you are curious about this, feel free to check out the SMS paper in detail, right? The ISCA 2006 paper. It would actually give you the detail on how this can be done. I believe this paper is also on our reading list as well. Another way you can think about this is instead of doing prefetching, we can use leader-follower execution as well. So the question is, can we use one processor just to fetch the data for another processor? The idea is I use the front processor to keep running ahead, and that running ahead would give you the address for the back processor, so that the back processor, whenever it needs the data, is already in the cache. If you think about it, the front processor is called the A stream, and the back processor, where you have everything in the cache, is called the R stream. A stream would fetch the data for R stream. The benefit here is you can actually kind of see all the address you have to fetch, right? And then get the address ahead of time for your program using the A string. And this can be really useful if you have a processor that does nothing right now, right? It doesn't run any program. So you can actually use leader follower and use that front processor to kind of prefetch all the addresses that you need to access. And now this idea used to processor, right? You can actually reduce the overhead and use only one processor through a technique called run-ahead execution. This actually is a technique that was a thesis of my advisor, Onamutlu, actually. And the idea just got the Test of Time award from HPCA a few years back. So the Test of Time award is the award given to idea that actually make a real industry impact, and it changed how we think about the way we run things. In this case, the way we use multi-core and the way we prefetch, and also the way we actually try to reduce the overhead of data access. So the question is, well, if you look at leader follower execution, you don't really need to processor, because when you have a long latency, like when you have a stall, you have to wait for a load or store to finish, right? The CPU is doing nothing, so you can continue fetching. The idea is, hey, can we run ahead in an out of order processor so that when you have a long load or store instruction that stall the pipeline, or to be precise, the load instruction that stall the pipeline, then you keep going ahead, try to prefetch the future address, and when the load comes back, you resume execution. And hopefully by the time your new addresses that you have to fetch is out there. So the overview of this, and again, this paper is produced in 2003, and recently got a Test of Time award at HPCA in 2021. And here's the overview. Basically, let's say you have processor running, right? So it's running. And say you have a load right here, and you basically have to stall because you're waiting for the data, right? And this is, let's say, where you finish the load. And you can resume running right now. The idea of run-ahead execution is this: while the processor is stalling and doing nothing, right? It would keep fetching, basically now keep fetching for new instruction. Which means that you might run into future load, like let's say this is load to A, finish load to A, right? This is load to address B. You see another load here to address C. And another address to load D, right? In this case, with one stall to load A, you already generate 3 additional requests, B, C, and D, to make sure that when you resume running, and you actually have to get the data for B, C, and D, it's already in the cache. And the more detailed design is right here, where you can see the highlighted portion. You need to actually now have the run ahead cache, and the shaded portion are what you need to actually add to support run ahead execution, including when you want to run ahead, you have to checkpoint your architecture register file so you can come back and resume execution whenever it has to it has the original loads data, right? So now that's about handling cache interference and also handling load and store in the cache level. The next thing is we want to be able to handle DRAM interference as well, because application can occupy more or less DRAM capacity, DRAM bandwidth, and the priority in which the schedule the request gets scheduled, right? So you can do things like DRAM partitioning. Split the DRAM into multiple channels or multiple banks and partition the DRAM for each application separately, right? And non-share bank would provide isolation from other application. You can also partition DRAM capacity to things like page coloring. So this is the classic OS techniques that you can apply. You can also do DRAM scheduling, as we discussed. You can have things like FR, CFS, right? Memory scheduler would determine basically what application are prioritized. And this ensures things like fairness for each application running on your system. For example, right, you can embed some application ID to your memory request, and each of the application in DRAM basically would maintain the characteristics of each application, and you provide different priority based on the request. We'll go into more detail about some of the work I've done on this direction as well when we talk about more of the paper-related ideas on the last week of class. You can also manage the page. For example, the operating system can determine what data should be stored in DRAM, right? And now you can control the application data inside the memory so that the page fault doesn't happen as often, because that takes a long time, right? This can be utilized when the memory is limited. For example, we did have some work in collaboration with team from Hong Kong and Huawei that look into like how do you maintain your application data on a phone in DRAM, right? So that when you open up the app, it doesn't really take a lot of time to launch the application. It doesn't take a lot of time to like start from cold boot or cold launch, and it hopefully improve user experience, right? The other thing is sometimes you have unpredictability of how much time does it take to access your data, because sometimes you cannot tell how long each load or store will take, right? Which means that if you cannot tell how long each load and store takes, it means you cannot tell how long a function call would take. It means also you can't tell how long a program would take. And some applications do have a hard deadline, like a self-driving car, right? You cannot really process certain things within the same time, within some unit of time, you might have a car crash, right? So the other thing is sometimes you have clients that pay a lot more money in the cloud, right, to guarantee certain amount of performance. So you might want to make sure that you have predictable performance. Performance predictability is still a very active area of research in both architecture and OS to actually provide some guarantee on how long a request would take. Right? For example, if you can provide a worst case guarantee for all ongoing requests that the operating system handling right now, right? This allows some application at least some load store latency guarantee. Right? But doesn't mean that you have application level predictability yet, right? Because that you have to coordinate with the OS. All right. The next thing that we'll talk about after the break, now that I talk about a lot of ideas and a lot of papers that have been looking into cache and DRAM, right? We'll switch gear a little bit and look at data coherency and how to ensure that, right? So let's do a 10 minutes break. We'll resume at 11 o'clock and we'll come back with data coherency as a topic going forward for the next part of this lecture. All right.